Yeah, so as Yao said, it's supposed to be very introductory. So if something's not clear, just say. And also I can adapt the topics to what you guys are interested in. Okay. So, and I'm not going to talk about new result. Today, all I want to do is try to explain the scalings and things like that, just the basic things. Okay. Okay. All right. So let's start with the KPZ equation. So that's a Carter-Purgy-Zhang. There's another KPZ in probability which has nothing to do with this. It's 1986. Okay. Equation. Okay, so this is an equation for a height function. So you've got function htx. Okay, so t is positive. It's the evolving height function, and x is in R. And it's supposed to satisfy the following stochastic PDE. dth equals dxh squared 8 plus dxh squared plus c. And maybe there's some coefficients in there. Okay. So coefficient, I'll call this one nu. I'll call this one lambda. I'll call this one root t. Okay. Now, the various things have to do with various parts of this fluctuating interface. So there's an interface here, and it's sort of growing this way by stuff attaching from the sky in this random way. The c here, c tx, is space-time white noise. So if you don't know what that is, that's a Gaussian, and it's completely decorrelated in space and time. So the expectation of c t1 x1 c t2 x2 is just a delta function t1 minus t2, delta function of x1 minus x2. Okay. It's not a function, it's a distribution. This extremely rough guy. Okay, so this says what's forcing the thing is just independent at every space and time point. And then it's supposed to have this mechanism here, which is a smoothing mechanism. Okay. This is forcing the random growth. This is the smoothing. And then there's the most important term, which is the nonlinear term. This is lateral growth. Okay, so let me explain why that's lateral growth. This is the important term. Okay. So what that means is that if you didn't have this, what you would just be forcing this thing with the randomness, and then there'd be some smoothing mechanism. The thing would sort of go like that. Okay. But the lateral growth is an effect where, let me just draw a picture, bigger, where the growth rate is not really in the vertical direction, but also in the lateral direction. Okay. So it's trying to grow laterally, okay, when things attach. Or in other words, the growth rate is depending on the slope. Okay. So of course, if you looked at the vertical component of this thing, then you would say that the vertical component was something like, well, in this picture, it would just be, the vertical component of the growth would be 1 over the square root of 1 plus dxh squared, right? So you might say that that would be the term for lateral growth. Does that make sense? Just the vertical component, if that thing was going in that direction. But if you want to, let's just call this thing f of dxh. Okay. So what do you want about f? Different things are going to have different mechanisms for the nonlinear growth or the lateral growth. And the key thing about f, basically, what do you think? It should be symmetric, maybe, in dxh. Not much more than that. The idea is you should expand this f of 0 plus f prime 0 dxh. Okay. Now, the f of 0 term, if you add f of 0 there, you can just remove it by a shift in the vertical direction. And the f prime 0 term, that would just give you a dxh. You can remove that by just shifting your frame of reference this way. So the first term you see in such an expansion, which can't just be removed by such a thing, is this one. Okay? So you just call this lambda, and you just add that on as your term, and then you just drop the rest. Okay? So it's a very naive derivation, but gives you this magic equation. Okay? So that term is supposed to encompass all these nonlinear possible effects that you get. You can say, well, why didn't I add dxh cubed or dxh fourth? It turns out that they don't. If you do, they just scale out, and you get this back anyway. Sorry? And the sign's completely unimportant, because if you take minus h, it just changes the sign here, only here. So the sign's completely unimportant here. Of course, the sign's important here. But not here or here, right? Okay. So actually, you can just choose standard variables here. So I'll just choose this to be a half. I'd like this one to be minus a half. It's just because that's the way it comes out of some models. And then this one I'll just call it 1. So you could just take this as your standard variables. Yeah. Okay, so Yao brought up an important point. The derivation is completely absurd, because the surface is actually like a Brownian motion. So dxh is just, xh squared is just infinity. We'll come to that. Yeah. Actually, so how do you see that? It's not the easiest thing to see. But suppose I drop the lateral growth term, and you just want to analyze this equation. Okay? So let's see where the Brownian comes from. If you want to solve this equation, okay, solve it without the nonlinear term. It's just an Ornstein-Uhlenbeck process. It's linear. You can just solve it. So you get h tx. I'll write this because this sort of thing comes in later, but I think everybody can do it. It's pt x minus y, h0 y dy. Minus y, and then you get c y dy ds, right? So that's what you would get for the linearized. It's linearized. Right? So that would be the answer, where P is just the heat kernel. So PTX. It's just e to the minus x squared over 2t by root 2y. Right? So that would be the answer. And you see the answer is just, well, it's just this linear thing of the noise, right? Now, if you look, there's no problem defining this. This is a distribution, so this is smooth, so you can just define this thing. And now, if you calculate ht x1 minus ht x2, take expectation of that squared, okay? Then basically, well, let's not worry about this term. So forgetting this term, you just get just pt minus s x1 minus y minus pt x2 minus y. Then the noise, but the noise squared, you just get this thing squared dy ds because of the delta correlations, right? So all the twiddle just mean I forgot the first term because I didn't want to deal with it. Say maybe h0 was 0, just to make it easy. Okay. Now you can just check this thing. As t goes to infinity, this looks like x1 minus x2. So that's telling you that the thing is looking like a Brownian motion. It's Gaussian, of course. It's just a linear thing of the white noise, right? So it's Gaussian. So this thing is basically behaving like a Brownian motion. Okay? And in fact, Brownian motion is invariant for the linear equation. Okay? So that leads you to believe that the thing is basically looking locally like a Brownian motion. Because on local scales, this thing doesn't control things. On local scales, the linear thing controls things. Okay? So locally, the thing actually looks Brownian. And that's why this dxh squared is infinity. Okay? Now, the amazing thing, this is completely amazing, and it's not something easy to explain, is that the equation without the linear thing also preserves Brownian motions. Okay? So that's true. So if you start H with a two-sided Brownian motion and let it run, then at a later time, you'll see another two-sided Brownian motion, a new one. And the only difference from the linear equation is that this thing will make the Brownian motion go up. And the weird thing is the minus a half, it still goes up. It goes the other way that you think it does. Anyway, all right. Okay, so that's a KPZ. What's that? Yeah, let's just make minus. It doesn't matter. If I don't make the minus, then later I'll make minus mistakes all over the place. Okay. We should differentiate that KPZ equation from the KPZ universality class. KPZ universality class is a huge collection of models. I'll give you a bunch of them, which all are supposed to have the same large time long scale behavior. Okay, there's this universality in d equals 1. We're just talking d equals 1 here. D is the dimension of x. So sometimes, because there's an x and a t, you should 1 plus 1 dimensions. Okay, that's the x and the t. Okay. So I'll just give you some examples. What? This thing called the Eden model. So Eden model, you have a two-dimensional lattice. And you have a cluster. Maybe you could start with a seed at the origin. And the cluster has a boundary. The boundary is all the sites in the two-dimensional lattice which are next to the cluster. And all those sites join the cluster at rate 1, Poisson clocks. Okay, so the cluster starts growing. You get this growing cluster. Okay, so that's called the Eden model. So after a while, you make a big picture. You get something like that. Yeah. Yeah. So if that's the cluster at some time, then there's a boundary. So here are the boundary points. And each one joins the cluster at rate 1. Okay? Well, of course, you can make variants of this. In discrete time, you could just have the cluster, and then each time you could pick a boundary point and join it, things like that. Okay, so that's Eden model. So at a later time, you have something like this, and well, that's the picture. Now, what's supposed to happen in Eden model? Okay. So the connection to that is that if you look in some direction, this thing is supposed to look like KPZ. Okay? KPZ was written down as sort of a continuum model of things like this. Okay, so now let me tell you what the scaling is supposed to be, because it's clear in this picture. At time t, okay, in the right variables, you should see this thing is about size t. So time t just meant when this thing's about size t. Okay. And if you look in this direction, what you should see is the thing is some constant times t. That's the size of the cluster. And then in this direction, you should see this fluctuation is. Okay? So it should look like something like CT plus, well, actually, minus some constant x squared over t, where x is now this variable, the lateral variable. And then here's the conjectural behavior. On top of that is this random stuff, the random fluctuations of the boundary. And they should look like size t to the 1/3, and then some. Where A is some universal stochastic process. Some universal fluctuations. Random matrix theory. Okay, so that's the conjecture. It's the Airy process. Or if you don't care about the x, it should be the GUE Tracy-Whittem distribution. Okay. So that's what one wants to prove. This is all conjecture. Sorry? No. I guess the existence of C1 is proved. The existence of C1, you can do it by subadditive ergodic theorem.
Even the next step.
No, you don't know. In Eden model, can anyone prove that C2 is positive or not zero? I don't think so. But you need to know the shape doesn't flat. I don't think it's known. Yeah. Yeah. It's not.
Is this supposed to be for any initial, any sort of finite initial configuration?
Yeah, that's right.
I guess if you started with like a half plane. So
Yeah, well, let's, okay. And if you did started with a half plane, okay, good question. Start with half plane. Then you, something like this going that direction, right? Okay. And you started here. This is supposed to be T, CT. Some other constant, I guess C4, oh. There's many constants here, sorry. C4. These are all non-universal constants, and I don't think anyone has any idea what they are. So this would be C5. Sorry?
It'll be the same as C1.
Yeah. I guess one could guess that this is C1. Yeah, that's right. Okay. That.
Because when I look sort of along the diagonal, there will be different
It's because this is drawn in the wrong direction. This thing isn't a circle. This thing isn't a circle. So if the way I drew it, it would be this C1. Yeah. Okay. Okay. There are some things you can say, but okay, they're not terribly relevant anyway. Now you won't have a parabola, of course. Okay, C5, T to the 1/3. C6. And now A1 is the GOE. A1 is the Airy 1 process. The marginals are GOE. So this is again conjecture. No, not really, is there? I can give you some explanation, but yeah. No. I mean, if you believe that this is an area 2 process, okay, then you know that the soup of the area 2 process minus the parabola is a GOE, and you can see why it would do that there. So that's why it's GOE. Okay.
Are these conjectures based on numerical computations?
No. No. So yeah, what are they based on? Well, if I give you, I have to give you a few more models before it's clear what they're based on. As we go through the models, then there'll be some model which actually degenerates to something where you can see it. Okay. But if I show you that now, you'll say, what does that have to do with this? Okay. So let me give you a couple more models first. And of course, the analogous thing is supposed to be true about KPZ. Some of which can be proved now. Okay, so this is pretty completely open, partly because the Eden model, you don't even have a surface, right? Yeah, you don't really want to do this problem because it really looks like this. You don't even know what's the height, right? But you can make a model like this where you do know the height, which is another of the motivating examples. So this is one could actually really start trying to do it. It's the ballistic aggregation, which is like a version of Eden where you have a height. So here you have Z, and particles are simply falling from the sky with Poisson processes at every site in the integer lattice. And they fall from the sky and they start building little towers. Oh, so I'm not drawing it very well. Okay. So there 3 particles fell at different sites, and then maybe a couple more fell here. Maybe one fell here. Okay. As such, it's trivial. And if they were just falling and building up, then it would be equivalent to the, I mean, you could scale it to the linear version of the KPZ. So the nonlinear effect is the particles are sticky in the sense that if you have one fall here, it sticks here and not just on top of this. Okay, is it clear what the rule is? So they stick to the sides. So they fall with Poisson processes. And stick to the sides. Okay. Now you have an actual height function. And again, it's supposed to be like this KPZ. It was one of the motivating examples for the writing down that equation.
But again, there's a problem with the height.
Sorry?
What's the height? Now the top line.
The top, yeah.
You don't
That's
care about this empty space.
Yeah. You just think about it like, if I have, so the height function now looks like this. Right? Well, you can easily write down the dynamics. The dynamics is that just at rate 1, you jumped either to the maximum of the height at the site plus 1 and the 2 neighbors. That's all. It's a simple thing to write down. But there's no result whatsoever. Of course, exactly the same things are supposed to be true, in the sense that if you start with a flat thing like I'm saying, you're supposed to have this. Okay. Okay, the next model, maybe you can't see here. The next model maybe people here are very familiar with, and that's ASAP. This is one of the ones which is semi-solvable, and most of the results are coming from. So in ASAP, the height function looks like this. Okay, it's over the integers. In every integer, you have either an up or a down. The slopes are just 1 or minus 1. Or you could think of this as a random walk path over the integers. Nearest neighbor random walk. Okay? And the rule is that one of these jumps to one of these at rate q, and one of these jumps to one of, oh, I should dot, at rate p. And we'll assume that q is bigger than p, and they're both q plus p is equal to 1. This is just a, make this easier. Okay? And that's the whole rule. Except that if anyone's ever seen ACEP, they usually think of it as particles. And the particle to height function picture is very simple. Where the thing is, where the slope's plus 1, you put a particle. No particle, particle, no particle, particle, etc. Okay? And then you can just think the particles are jumping this way at rate q and this way at rate p, but jumps to already occupied sites are forbidden. And it clocks just starts again. And it's exactly the same thing. Okay, so you could either think of it as the height function or of these particles. It's just the same. Okay. Okay. Of course, you could make lots of models like this. You can see that it's extremely general. Okay, so here's another class of models. It seemingly look completely different. These are directed random polymers. So the directed random polymers, at first you won't even see where's the height functions. So just forget everything you saw. These are models of random walks through a random background. Okay. The random background is called Cij, and it's on a two-dimensional integer lattice. And I'll weight the walks by an energy, which is just what the walk sees as it walks through this two-dimensional lattice. But they're directed. Okay. So let me draw a picture. Here's time, which is called n. And then you have this random background, and the walk goes, well, this is the nearest neighbor random walk. Which just means it either jumps one up or one down at each time. Okay, but they're directed because there's a direction. Okay, I'm drawing it badly. Goes through this thing. And it collects the Cij's wherever it goes through. Okay, but they're directed because this I keeps increasing. Okay, so that's the energy. You divide this by a normalization, Z beta n. The normalization is just the sum of such things over all such walks. And now you have a probability measure on these random walks. Okay? Given by this random background. And the random background, let's choose it to be IID, random variables. And more or less any distribution you like. You need a few moment bounds, but okay. So take your favorite distribution, and I'm sure it'll work. Okay. Okay, so that's the model. Is it clear? It's a model of walks, and it doesn't seem to have anything to do with that. Okay. Now, the way I drew it, they're starting at 0, and they're going to Okay, so let's say 0 to x. So there's two models, one in which you decide where they're going to go, and one in which you just let the endpoint dangle free. Okay? So the free endpoint is called the point to line, directed random polymer. Or the other one, where you fix the endpoint, is the point to point, directed random polymer. Okay, so you've got two different models. And of course, the z will depend on whether you do point to line or point to point, right? So you could just say, well, I put an x here if I decide it's point to point and it's going to the point x. And if you drop the x, then it's the point to line. Okay. Blackboard problem. Go here. Okay. So, well, first of all, if you first see this problem, it's well defined. Everyone's clear about the definition, right? Somehow I failed to do it. Okay. If you first see this problem, you might imagine that for a very small beta, it looks essentially like a random walk, right? Or maybe you would turn on beta, and the more strength beta had, the more it would start to see this random background. But that's completely false. So what happens is, in one dimension, it's strongly localized for any beta. So what this thing looks like if you simulate it is it finds a favorite path. There's sort of a favorite. And it just sticks there. There's almost no randomness. It's got its favorite path to go on, and it sticks there. And the fluctuations of this path, you might think they would be about n to the 1/2, because they'd be like a random walk, but that's false. You look at n to the 2/3. Okay? And the thing's extremely unstable also. If you change beta and you change n, this path just changes to a completely different path. Fluctuates all over the place. But for fixed beta and fixed n, all the paths are very close to this one. Well, it's not that they're all very close. There's maybe a ghost path over here where a couple of them go.
Is this a fixed background? You choose a
Yeah, you fix it, take a fixed background. Okay? Then what it does is it sort of finds its favorite way to go through that fixed background, which, by the way, is not the minimum energy. And, well, maybe it's the minimum energy. It's the minimum energy over those paths. Yeah, there's a subtlety here. Okay. Okay. Yeah. It finds the minimum energy over such paths. Yeah. Yeah.
Finds the minimum free energy.
Yeah, it finds the minimum free energy over such paths. That's what I'm trying to say. There's a subtle thing I'm trying to say. It's not just the asymptotically. It's not just the minimizer. It's a fight between entropy and minimizing this thing, and it's not what you think, because otherwise, as beta changed, it wouldn't flip around. So what happens is that as beta changes, if you change beta, that changes the war between entropy and minimization, and you really see this thing flip all over the place. It goes completely crazy. Of course, as beta goes to infinity, it'll go find the minimum path. But it's not just what you might think if you're naive is just that there's a minimum path, and as beta gets large, it concentrates more and more and more on the minimum path, and that's not at all what happens. It goes all over the place looking for this thing. That's what I was trying to say. Okay. Good.
And in fact, if you go long enough scale, it will go up and down across the axis, right? You draw it like it has one direction.
Oh, yeah, yeah, yeah. No, sorry, that's just a bad drawing. Yeah. Yeah. Okay. All right. Now, of course, the question is, what on earth does this thing have to do with all the things that I said before? Where's the growth model? Okay. So in these models, the log of z, z's the partition function, and the log of z, beta, I'll put a t there. T's n. It's the same thing, really. Let's call it h, gx. Is the KPZ-like quantity. It's the height function in this model. Okay? And it really behaves KPZ-like. It's like it satisfies a discrete version of the KPZ equation, and you expect all the same things. Okay? So in other words, the partition function is supposed to be e to the constant t plus this thing. Okay? If, so what are the two things? Point to line corresponds to this flat interface. So you'll see GOEs. And point to point corresponds to the, I don't know, seed or the curved thing. So you'll see GUEs. Okay? So there's a point to point. You got GUE and point to line. GUE.
What is the height function point to line? Because x seemed to be, what you wrote down seemed to just use point to point.
So in the point to line case,
Maybe want to say
oh,
point.
line to point.
You can fix x.
Yeah, if you want, if you want, you could do this.
Oh, okay. It's really line to point.
Yeah, if you want. It
You
doesn't.
don't have to, I understand. Let's just be line to point to line. If one end fixed, the other one's free.
Let's do. Let's say. Okay. If I do point, no, this is good at y. So here's a point to point, okay, and that'll be GUE like. Now, if I let y be free, the claim is that the whole thing doesn't depend on x, which is kind of obvious because it was free, and then it'll have that behavior. Sorry? The picture's probably not that great. There's also some nice universal quantities here. If you do point to line, then this endpoint should be n to the 2/3 times some other universal distribution, t, call it, right? And that thing, we know what it is. That's known. But because this is supposed to be an introductory talk, I'll say some problems which aren't known. So let's do point to point. So if this was instead point to point, let's go 0 to 0. Okay? And now you look in the middle, say, or any place you want. Then this distance, so this is n steps. This distance will be, again, n to the 2/3 times some other universal. It's not t. I know, t prime. The polymer midpoint distribution. It's not known what it is. You could write down a variational formula for it. It's the supremum of the sum of two Airy processes minus a parabola. But it seems to be very hard to find the distribution of that. So find a formula. Okay. There's another question, which is that if you think of polymers going to y from x, or maybe x prime, okay, Well, you could well imagine what they're going to do is they're going to do something like that, because there's probably a good region here, which is why they went there, right? Okay. So there's some distribution there, which is also unknown. It's another universal distribution, the polymer coupling time. Okay.
Don't even know the exponents?
Sorry?
Don't even know the growth scaling exponents?
Of that? Yeah, I think you could calculate what it is. It's of order n. If those are. Sorry? Yeah, yeah.
Exponents exponent to like 3 halves or something? Or?
Yeah, because x minus x. 2/3 or 3/2. 3/2 probably. Yeah. Okay. Okay, let's now I can make you a little bit of an argument for the third and the 2/3. Okay. So what's the argument for the third and the 2/3? Okay, so now you should take a bigger picture and think of all these models. Actually, the dimension wasn't so relevant here. You could have done this in higher dimensions just by making the j variable to have more dimensions than 1, right? So if this variable takes values in a d-dimensional lattice, then you've got the 1 plus d-dimensional directed polymer. And so you just have a d-dimensional random walk here, right? And the corresponding thing would be a d-dimensional KPZ equation, which I didn't write. So I'll just write it here. So in d dimensions, the KPZ equation, it's not well posed, but it doesn't matter. It would just be this. Anyway, discrete analogs of it make sense. That's the noise. So that's the analog in higher dimensions for the free energies. Okay. And you want a sort of general relation between the scaling exponents, which are this guy here, which I'll now call zeta. That's the wandering exponent. And the one I covered, this one here, this one here. Let's write it here. That's the fluctuation exponent. Right? And here should be the wandering exponent again. Okay. And you want to find general relation between these. Now, the very simple argument is that this polymer here should go to the optimal place in this problem. It's the x. And it should look to optimize this thing. So you basically have a battle between x squared over t and t to the chi. So t to the zeta squared over t should be roughly the same as t to the chi. Okay? Just from the parabola versus the t to the chi in that conjecture. Okay? Which tells you that 2 zeta minus 1 is chi. And that's supposed to be true in all dimensions, and that's called the KPZ relation. Okay?
Would you explain that again?
The problem is if you probe, it's going to fall apart because it's not a very satisfactory argument.
I just want to see the bear.
Yeah, yeah. So the idea is that the polymer is looking to optimize the place in the random interface to go. Okay? And if you believe this with some fluctuating guy here, okay, then what it has to do is it has to choose the x okay, for which this thing is roughly the same size as this. And x is called t to the zeta. So t to the zeta squared over 2 should be about 2 to the chi. And that says this. Okay?
You're saying the second and third term should be roughly.
But yeah, it's just a balance between those two guys. And that says this exponent should match. Okay.
Why they should be about the same? I don't understand.
Because you should think of this, the particle, its endpoint is just the place to find the maximum or the minimum energy at the target place, okay? And that energy, the free energy, is just this thing here plus these random fluctuations. So you think of this random energy surface, and it just looks for the minimum, okay? So it just basically has to optimize this thing versus that, okay? Well, the way I wrote it, I'm sorry, this is why I get in trouble with science. It wants to maximize this object, okay?
But you didn't explain why they have to be of the same size. I mean,
Well, if you want to maximize this in x,
but they said about location of the x.
yeah, sorry, and in higher dimension, the only difference is I should write that. Yeah, sorry. Sorry. I just want to find the size of the x,
Yes, that's the size of x.
which maximizes that. And x here, this is x, is called t to the zeta. Okay? So the size of x, which maximizes, is just the maximizer there, which is x squared over t should be about t. Okay?
You could just differentiate an x and set the derivative equal to 0.
Yeah, I didn't want to do this because the argument's too rough to differentiate it. So it's like the argument's much more floppy than that. Now, okay, but that's basically the idea. Why? Okay, I'll show you another argument about these things in a sec.
And this is presumably sometimes not true because there's logarithms or something.
Oh yeah, sure. So in two dimension, this would be.
2 dimensions, there's
Yeah, there'd be log corrections. Yeah. But I guess otherwise, except for 2 dimensions, it should be okay.
higher than 2 you have.
Okay. Anyway. Yeah, so but then of course you might wonder how do we get the 1/3 and 2/3 in 1 dimension? Okay. So this is supposed to be true always, except for the logs. And in 1 dimension you have another thing, and that's that we as I showed you, the things are supposed to look like Brownian motions on a large scale. And that's the thing which tells you that it has to be. So that means this fluctuating quantity, as t goes to infinity, should actually converge to a Brownian motion. Okay? Because that's the invariant distribution. So locally, you should see a Brownian motion there. Well, how are you going to see a Brownian motion? The only chance to see a Brownian motion is if this zeta was twice chi. So Brownian motion implies this is g equals 1. Zeta equals 2 chi. And that's why you get zeta equals 2/3 and chi equals 1/3. So that's the basic argument why those things.
This is what's missing in higher dimensions,
Right. So
This invariant measure.
right. So in higher dimensions, if you look at this, you see it's complicated because these models, except if you're unbelievably lucky, aren't even going to have an invariant measure. Right? So you got to be pretty lucky there. Okay? But there are special cases. So but what's supposed to be true is that the invariant measure should look like random walks or Brownian motions in 1 dimension. Okay? But in higher dimensions, you don't even know what they look like. Now, you've got a problem because you don't have a continuum model for which you're allowed to try to check what's the invariant measure either. Even if you formally write down this equation, you can't find an invariant measure, but the equation doesn't make sense, so it wouldn't work anyway. So you're sort of stuck. Okay.
You're very lucky when you can find an invariant measure.
Yeah.
That's
You're not suggesting the invariant measure doesn't exist.
Oh, no, no, sure. We want to know what it looks like. Do you have any idea? That would be great. Nobody really seems to know what it looks like. I mean, people have some ideas a little bit. Okay. Anyway, so you can't repeat this argument, and therefore it's not known what these things are in higher dimensions. It's only known by computer simulations. And you get, like in 2 dimensions, you get chi equals 0.24 or something like that from computer simulations. It was thought to be a quarter, but it seems to have been ruled out by computer simulations. Okay.
So it's not supposed to be a fraction, right? It's not.
There's no particular reason to believe it is. Yeah. It's probably just some funny number. But it is, I mean, there's even a question whether it's independent of beta, right? But I guess it should be. Yeah, why not? Okay, I only have a couple of minutes, so let me, okay. I'll leave to next time some things, and I want to show you another model. It still a little bit begs the question of where the GOEs and the GUEs are coming from, right? Here's a special model. Yeah, I'll draw it here.
So, Jeremy, this can't be done in the case of Poisson?
Which one? This.
Yeah.
So what do you want to do? You want to have a Poisson field with Brownian motions going through and the spread out potentials? I mean, what do you mean this? It's true. The whole picture is correct, but it's not a solvable model. No.
Yeah.
No.
You're going to tell us the Poisson model you can't compute it with?
I'll tell you the computable models. Yeah, eventually. I don't know if I'll get to it because I only have 5 minutes. I'll tell you a couple right now. Okay. Okay, so computable model 1. So all these computable models are going to be as beta goes to infinity so far. Then later I'll do more computable models. Okay. Now as beta goes to infinity, of course, 1 over beta log z is just going to converge to the minimum of the guy upstairs, right? So you just get the free energy, which is just the minimum or minus the minimum of the sum of right, over the x. As beta goes to infinity. And those models are called last passage percolation. Okay. Now there's a special case, and it's written in a slightly different way than this, but it's morally exactly the same. And you could probably map it onto one of these if you wanted to. Let's take the maximum over upright paths. I'll show you what those are in a second. Of the sum of Cij. Okay, so an upright path, the geometry is just a tiny bit different. It should just go like this. Those are called upright paths. Well, okay, it can go this way. Sorry, I was drawing one path. Okay, so upright just means it either goes up or right. Okay, so the connection of these to those is by turning this 45 degrees. That's all. Okay. But because this is exact models, we have to be very precise here. Okay, so you take upright paths and you sum theCij's maybe from 0, 0 to a point mn. Up here, okay, and then you've got this free energy. Okay, so this is the sum over the path, and then it turns out, and this is the miracle. This is miracle 1 of the entire business. If these have geometric distribution, then it's solvable. Okay, so then this free energy. You can actually compute exactly the probability distribution, and it's given by a Fredholm determinant. Okay? So the probability distribution of this is given by a Fredholm determinant.
Calculation is non-intersecting path.
Yes, this uses the non-intersecting paths. That's right. Okay. Sorry.
Precisely, what do you mean by geometric distribution?
Yeah, so the probability that C is n is just p to the n minus 1 minus p, I think. P to the n. Sorry. For some p.
And real?
Sorry? N equals n equals. Yeah, it's an integer value distribution with those. That's called a geometric. Anyway, so there's another one too. If they have an exponential distribution, it's also computable. So there's these two special cases where it's explicitly computable, and they're given by Fredholm determinants because of a connection between this and non-intersecting paths, or if you like, randomly growing Young diagrams. You have exact formulas. So you get an exact Fredholm determinant, you scale that Fredholm determinant in the way that I showed you, and you get the GUE distribution. So that's how it was discovered.
Non-intersecting path. What non-intersecting path has to do with distribution?
Ah,
Non-intersecting
no.
path is supposed to
No,
be
no. Yeah, it,
You cannot see it in 1 second.
yeah. It's, you see, what are the non-intersecting paths here? They're not these paths. They're various free energy levels. So it's a complicated thing. You can't explain it in 2 seconds. Okay. Well, you should think if these are exponential, then it's TASEB. And then TASEB you can think of as non-intersecting paths.
I don't want technical reason.
It's only technical. Is there anything but a technical reason? I don't think.
So the path is really has no physical meaning. You look at free energy and then look at different levels, and this is how you artificially construct.
That's right. It's a very non-obvious construction. What he's talking about, the different levels, so that the top level is the free energy, which I told you about, which is the minimum of that. The second level, so you could also imagine a free energy where you had 2 non-intersecting paths doing this, okay? And that would be another free energy. And then the differences of these free energies for the various levels of non-intersecting paths give you a bunch of lines, and those lines are a non-intersecting line ensemble. Non-intersecting line ensembles become determinants by the Carlin-McGregor formula, and that's where the determinants come from. Okay? Does it make sense? But it's not at all obvious why those should be non-intersecting lines. It's a miracle. Okay. Let me give you one more model and then we'll stop. Okay. So there's another solvable case, which, again, it's another miracle. All these things are miracles. Now, the KPZ can also be thought of as a polymer. It's the continuum polymer. I'll put it in quotes, where you run a Brownian motion through the space-time white noise. The only problem with this guy is it's a little bit ill-defined. It's not terribly ill-defined. It just needs a rather straightforward renormalization. You can make sense of it. So there is a random polymer model like that. Okay. And its free energy is KPZ. I mean, KPZ equation. The KPZ equation is the equation for the free energies of this particular continuum random polymer. Now there's a nice discretization of this thing, which isn't obvious at all that it is, which is called the O'Connell-Yor polymer. Which is another one of these solvable guys. And I'll just describe that quickly and then we'll stop. Okay, so in the O'Connell-Yor polymer, you also look at upright paths, but now in continuous time. Okay, so the path goes for a while, and then at some time, S1, it jumps 1. This is distance 1. It goes in some time S2. It jumps up again, 1, etc., etc. Okay. So that's the polymer path. So the polymer path just, there's time 0 up to time t. Oops. And then you have n times. And we'll call Sn equals t. Okay, so that's a path. It's just these random, if you like, times, and then jumping 1. And then the energy is minus B1 S1 plus B2 S2 minus B2 S1 plus Bn Sn, which is T minus Bn Sn minus 1, where the Bi's are independent Brownian motions. Okay? So this is the energy. This is h of the path. Is equal to minus this. Okay? That's the energy of such a path. And of course, you just weigh them, e to the minus beta h divided by z beta. And Shm. Okay?
You can't quite read the indices from here.
Of which one? So you take a Brownian motion,
Yeah, that's
and
B1,
you
and then you have
B1, so you can think of this as B1 S1 minus S0. So you collect the Brownian motion B1 here, and then here you collect Brownian motion B2 from S2 to S1, and here you collect Brownian motion B3 from S3 to S2, the increment.
So those are just the increments, independent Brownian increments.
Independent Brownian increments. The BIs are just independent Brownian motions just given to you at the beginning. Okay. And then that's the energy, and that's the weight of the path. Okay.
So is it S is dynamic variables or?
Sorry? You can just think of S as the labels of the path. So S1 through Sn minus 1 tells you what the path is. That's all you need to describe such a path. Right?
Later with the sum over all possibilities.
Right, well, the Z is just the sum over all such paths, going from 0 to some x.
Well, collections of S is the net of T.
Yeah,
Or, yeah,
adds up to, yeah,
or, yeah, collection of S.
right. And here, the position here is clear, it's T, right? There's nothing, that's where, sorry, it's N, it's N. The position at the top is N, so. No, time's continuous. Time's continuous. So Z beta N is an integral over all such S's between 0 and T, ordered, of the thing at the top. And the Brownian motions are given to you at the beginning. That's the random background. Right? So the Z, of course, depends on all those Brownian motions. Now, this guy's, if you want to see the picture, of course, pictures like this, all you do, you just turn them sideways, right? And then it's the old picture. But actually, this one, you're better off, instead of turning it sideways, just skew it down so it looks like this. Right? So skewing, I just mean make a affine shift down. And then just make it so that it ends up at 0, so it's 0 to 0. Okay? All right? And so a path just looks like that now. Right? Is it clear? And think of N as about T, if you like. And now, if you look, you can just think of the guy here is collecting this Brownian motion here. You could just think of him as collecting the white noise in this box as he goes along. Okay? And then this one collects the white noise in this box. Now, if you integrate the white noise over that box, of course, you just get a Brownian motion from here to here. Okay? So all this model is a funny discretization of the continuum random polymer using these sawtooth paths instead of Brownian motions. Okay? So you can see immediately it's a discretization of the continuum random polymer. But it's very special because as beta goes to infinity now, you're going to get the maximum of those things, right? So as beta goes to infinity, you get the maximum for 0. I'm running something a little bit obvious. Right? Clear. But this thing equals GUE in distribution. That's Baryshnikov. Or even
That's n by n GUE, it's a finite dimension.
yeah, sorry. Yeah. It's exactly an n by n GUE distribution. It's the top eigenvalue, and in fact, it's even more than that. If you vary the t, it's the top line in the Dyson-Brownian motion for GUE. So here you have one which you can just see exactly that it becomes the GUE as beta goes to infinity. Okay. So maybe, sorry, I went a little bit over. Next time I'll talk about some models which are computable, which are at beta finite instead of beta equals infinity.